So, thanks for the organizers for giving me the opportunity to talk about some relatively new application about homogeneous dynamics for quasicrystals. It's a joint work with Minkowski, who is going to be a postdoc at Rutgers University, and Weiss at Tel Aviv University. So my talk will split into two parts. First, I want to give you some general introduction about classical quasicrystal. So I'll tell you about two theorems of the 70s. And in the second part, I'm gonna prove some classification result to you, which are not too difficult for people who are experts in linear algebra groups, but since we aren't, we are still happy with the result. Okay, so I'll start with yes. I'll start with defining to you what a Delone set is. A Delone set is some discrete point set in some metric space where you force to have two properties. The first one is that it's uniformly discrete. So it means it's, you have your point set. Then there's some radius, small r, so that between 2 points you can always find a ball which does not intersect the point set. And the second property is that the set should be relatively dense, which means that if we choose a bigger ball of radius big R, then we'll cover the whole metric space. So right, these things are clearly related to packing radius and covering radius. So one particular point set are the points of the Penrose rhombus tiling, right? So take the point set coming from the corners of those two different colored rhombi, and so by using the fact that you have this tiling, it's pretty easy to see which small r and big R you have to find. And okay, so this part, right? So so the point of this the point set is that it's highly non-periodic, and Penrose the first to find such tilings of the plane. Right, so, but I mean, for my talk, I don't really care about the tiling, but just the point set of this Penrose set. So one way to kind of understand those general point sets is by looking at patches. So a patch, right, so you'll fix some T naught or T, and you will ask. So if you have your point set, so you look at all possible balls centered at the point set of radius T, and you ask which configurations can you see, right? So I don't know, so maybe to make it a bit more visible, it's good to draw the associated spider. Okay, so blue is maybe bad. Green is visible, right? So right, you can draw this spider and ask which possible spiders you see in your point set. So we call these T patches, right? So here I try to find some T patches. So there are two kinds here. So first I have the purple one, right? So you may see that you can actually find more of the patches as associated to the purple one. Like here's all the one. And here I marked a different T patch, which is not up to translation, the same as the other ones. And actually, I was not able to find this particular T patch a second time in this picture, and you asked, maybe you have some rule of how often to find a particular T patch. So before going into that, I want to mention some theorem from 76. So you take which is due to Delone and its co-authors. So Delone was the first one to introduce this condition of finding small r and big R. And they prove that if you have this pointset, then there exists some T naught, so that if you look at all T naught patches and up to a symmetry, so here the full symmetry group of Euclidean space, so translations and rotation. If you only see one patch, then actually this pointset has to be very structured. It has to be a single orbit of some lattice in the symmetry group of Euclidean space. So they call this the local criterion for global regularity. And let me remark that these people actually consider the more general case of constant curvature metric spaces, right? And you have to replace lattice, since we started with the Delone set, by some co-compact lattice. Okay, so that's his historical remark on how Delone set came about. Then, okay, so Weiss asked the question of if you look at the holonomy vectors of the saddle connections of translation surfaces, then, right, so these things, right, so these things are particular points in the plane, and he asked when are those Delone, and so there's some answer for particular lattice surfaces. So instead of defining to you what a lattice surface is, I'll just rephrase it. So this question was answered by Rühr a couple of years ago, which says that if you take a lattice in SL2R and a point and act with a linear action, you ask your pointset, your orbit to be discrete, then there are two things which can happen. If gamma was arithmetic, then this orbit cannot be relatively dense. So think of primitive lattice points where you find arbitrary big holes. And if gamma is non-arithmetic, it turns out that this pointset cannot be uniformly discrete. Okay, but I mean, so you can find translation surfaces which have saddle connections being a Delone set by taking some slit torus cover, which you glue at the slit, and this if this the second point is algebraic, you kind of find some union of two lattices, which turns out to be Delone. Okay, so after having introduced to you what a Delone set is, I want to introduce a Millet set. So Meyer came up in Dani's talk in the beginning of this week, and this book which Dani mentioned, is the book where he introduces the following property. So call a Delone set Meyer if the different set is inside the original set plus some finitely many translations. Okay. So obviously he didn't call the set Meyer. He called such sets quasicrystals. So Meyer sets are nice because if you take, so you see that the lambda turns out to be a lattice if and only if this finite translation part is trivial. So we really want to think of this as a generalization of a lattice. And there's a recent, like in the 90s, second description. Lagarius proved that a Meyer set is, a Delone set is Meyer if and only if also the different set is Delone. This is a weaker assumption on the set, but it turns out it has to be actually of this form. Okay, so what did Meyer do with such set? So he proved that any Meyer set is a subset of some cut and project quasicrystal. So I have to tell you what a cut and project quasicrystal is. So we've kind of seen this construction in Amos' talk. But so here we take the lattice in R2, which comes from this square root 2 construction, and looking at its involution. So and we'll take some window set. We take this window set and look at the slab, and we'll take all the points which lie inside the slab and project them to the horizontal axis. So I shall call, so I'll, right, so this is again some very strong rigidity. With the result, you start with some pretty general set, but actually it has to come from some projection construction of some real lattice. So this was 72, and this theorem was kind of forgotten for about 20 years. Sorry, you yeah. So I think you can take subsets with infinite the different set, right? Yeah. Okay, so let me remark that he proved these things with harmonic analysis, but my talk will not contain harmonic analysis whatsoever. I also don't know the harmonic analysis part of this. Okay, so I'll give you a formal definition of cut and project, like a quasicrystal. First, we start with the cut and project scheme, where we don't have a window yet, but we start with data consisting of a lattice, curly L, which sits inside some product space, RD to the times A, where A is some locally compact group. So think R to the M. And I want to introduce a notation for the natural factor projection, pi and pi internal. Right, so this RD I will usually call physical space, because it's the space we'll see the quasicrystal, and this A is called internal space in the literature. So besides this triple, I'm gonna require two properties, which I denote by I and D. I means that the projection to the physical space, if you restrict to your lattice, is injective, and the property D, which says if you project to the internal space, it has to be dense. And so here the assumptions of a cut and project scheme. And now we also choose a window, which is a subset of A. And we look, right, again, we'll take the lattice, we take physical space times the window, and we project all the lattice points which fall into this thing, and lambda will know my point set in RD. So in general, I call this a cut and project set. But to have that this thing is Delone, you have to assume that this window is thick in the sense that it has non-empty interior, right? So if you don't assume that, then you may lose the relative denseness condition. Okay, so from now on, I will usually assume this and will call the corresponding set a cut and project quasicrystal. Okay, and the notion is kind of good because it fits with this theorem of Meillet. So, okay, so Meillet used this theorem to, so he said, so suppose we start with some lambda, which has some dilation in variance, some theta, some scalar, which is real algebraic, and using his embedding theorem, he proved that there are very strong restrictions of what theta can be. It's either piezo or solid. Then about 10 years later, I think basically more or less unaware of Meillet's work, de Broglie showed that the Penrose tiling I showed you in the beginning of the talk is some cut and project set, the cut and project quasicrystal, and Pleasance more recently kind of pushed this thing of taking some algebraic construction and study the corresponding cut and project quasicrystal. And so the square root 2 construction falls into this general framework of Ergodic numbers. So we'll fix some number field k. O is its ring of integers. We'll look at all possible field embeddings. Ks is associated Minkowski space. And so if you embed O in the Ks, it will be a lattice, and the same thing you can do for higher dimensions. So then we'll take some completion, take some real subspace, and Rm, which will be the internal space. It's orthogonal complement. So we write the Minkowski space as Rd plus Rm. We choose some window, and we'll get a Cartan project set. Okay. So of course, the Cartan project scheme has recently looked in a more general framework. So I want you to recall Armour's first lecture. And from the harmonic analysis side, some people from the Technion, so Björklund, Hartnig, and Pogodelski, kind of started to do the classical quasi-crystal harmonic analysis part with non-commutative groups. And I also have to remark that the Cartan project scheme is kind of a very natural thing for number theorists. Right? So anyway, so Bobotsky, Phillips, and Sarnax used the periodics to find nice sets on the sphere. And there's some paper by Ellenberg Venkatesh who pointed out that homogeneous dynamics can be really used to study various problems. So one particular I want to mention is the problem of finding and counting primitive integer points on large spheres. So this was a kind of studied recently by Acker, Einsiedler, and Shapira. So they look at so the sphere is some homogeneous space. You look at its S-adic cover, and given some primitive point on some sphere of some integer radius, then you can construct more primitive points on the same sphere by looking at a projection of some orbit HV, which is the stabilizer group of V in this big group. And you can kind of choose this window and project to the sphere. And they prove, okay, so if you take the point sets, the gamma v's, as v goes to infinity, so maybe you fix your prime, and if the norm, or the norm squared is not divisible by p, then they show that the point set will equidistribute when projecting on the unit sphere. I also want to quickly mention that it's actually useful to look at sets which are, or to look at window sets which are not, which may have non-empty interior. For example, if you take your internal space to be the finite ideals, then and the window to be the boundary of the unit void, then you can construct the primitive lattice points. Okay, but so again, right? This set won't be a Cartan project, a quasi-crystal in my sense, because it's not relatively dense. Okay, so I want to return to the patch problem. So sometimes we am asked, okay, so the goal is to define some patch frequency. Okay, so we fix some patch in the the pointset. And so we'll take some fixed ball, Bt, centered at the pointset. And we asked if we take some huge ball, so small t, it goes large, and how often do we see this particular patch P inside this ball? And so to make the frequency well defined, one that sometimes has to assume more assumptions on the window, so which will be satisfied if the window is open. Okay, so just think of the window being open. Okay, so the goal from me is to give some counting result for patches. And here's our first theorem. So, okay, so I will introduce to you in the second part of the talk what a random quantum project set is. And we can prove that for some random quantum project set. So currently we have to restrict to some rational type. I'm also going to tell you what it means. But if you have that, then there's a precise asymptotic, right? You have the okay. So so the frequency being well defined. Here you have the main term, and the theorem is something about a polynomial error saving. So these are like theorems on patch frequencies. So there's clearly some history. People have proven similar theorems, but their notion of random is differently. And let me also note that if we can change this Pt to some more general set, which okay, so the point being is, so maybe I have some second picture, that counting the patches is the same as counting points in the cover. Okay, so here's internal space. That's physical space. And I see here some patch. Then, which comes from, so here's the slab. So that's a window, that's a slab. Right? These come from some points. So there's some observation to be made that if you right, so here's the center of the patch called Y, and so suppose I have here some second patch associated to some Y prime, then you're gonna see the same the patches if the lift of this Y are actually close together in the upstairs window. So using this observation, this patch frequency count reduces to some counting of the lattice points in this big ball or some general monotonic set, a sequence of monotonic sets, times some special window is associated to this patch. Yeah, and okay, so and we apply Schmidt's theorem, which appeared quite often in the last 2 days to do that. I mean, no, so we restrict to the quantum project. Yeah, I mean, what if you have some weird Z whose the volume goes to infinity, but there's no patch inside. The frequency will be 0. But I mean, yeah. Yeah, so I know. Okay, so there's some further assumption on the window set, because it turns out, right, this. So we have to, I mean, Schmidt's theorem is something about monotonous sets, but those sets, those sets will not be monotonous. So in particular, here you do not see the square root cancellation, but it will be some, again, some kappa, which will depend on the boundary on. Okay. So I'm gonna start the second part of the talk. Right, yes, thanks, right. Yes, I missed to say that we're gonna only look up to translations. Yes, thanks. Okay, so the plan is to tell you what a random cut and project set is. So Markov and Strombergson have this wonderful idea of taking the SLDR action on the physical space. And right, so okay, so we have our cut and project set, which comes from this L, some letters in R d to the m, which so d to the m is now n. Sorry, I didn't write this. N is d plus n. I assume that my lattice is unimodular. So Xn will be the space of unimodular lattices. And since this V is supposed to act on physical space, it will be contained in the top left block in SLNR. And I'll take the orbit closure of this SLDR in the M-in space of unimodular lattices, which by Wagner's theorem will be given by is some homogeneous space. So the group which pops up, I'll call L prime. And now Markov and Strombergson introduce the space of quasicrystals by looking at all cut and project sets. So Y is a lattice in Xn, and we look at all cut and project sets which come from this orbit. And since we have a probability measure upstairs, we'll push it and say that this German Q has some probability measure. And this notion of random is now taken with respect to this M or mu Q. So Markov Strombergson actually considers some more general construction, which is more natural. In particular, if you want to construct the Penrose, the tiling. But I mean, yeah. But for my talk, I'll restrict to SLDR. And I also want to remark that for almost all Y, we actually have a cut and project scheme, meaning I'll have these two assumptions satisfied I told you about. So, questions? Okay, and you can ask, okay, so you have now this algebraic group problem. What are the L primes which can appear. And okay, so right, I'll identify Xn with this homogeneous space, and I'll rewrite this L prime curly L as some G L, where L will be defined over Q. And our first theorem is that L is almost Q simple. Yeah. And once you have that, you can apply some classification theorem to say that if you pass to the simply connected cover, so it has to be some restriction of scalar construction. And since we know that this L prime contains this SLDR, there are just two possible cases. And the restriction of the scalar construction has to come from a real number field. So I plan to prove to you theorem 1. I mean, the theorem 2 is just the citation of well-known theorems. Okay, so so if the dimension of a physical space is bigger than dimension of internal space, so D is strictly bigger than M, then already marked up Stromberg's nu, okay, the thing you get has to be the whole group. And there's some unpublished work of Oliver and Sargent, who I guess was also aware of this theorem. And for us, it was still kind of unhelpful to have some conversation with Manfred 2 years ago. Okay, so the proof for, so the important thing is the following lemma, which kind of will tell you how these assumptions nicely come into play. Okay? So I'm gonna introduce some more notation. I'll call a vector space in Rn curly L rational if L intersects it in a lattice. And then the lemma, the first part of the lemma, will tell me that if the projection to internal space is dense, then there's no proper L rational space which contains Rd. And if and the second property, the projection on the physical space is injective, then physical space, sorry, then internal space, you cannot contain a L rational subspace. So once we found those two properties, we can introduce the third property, L, which says that there exists no proper L rational subspace that is L prime invariant. And then those first two properties will imply the third property. So I'm gonna prove this to you. The proof is by contradiction. So A, I suppose not. So I'm gonna have some rational subspace W. So Rd, which is contained in W, and this one is L rational. Then the orthogonal complement will be L rational and contained in Rn. And you start looking at the map, right? So lattice and intersecting Rn. We project to this physical space. So by assumption, this is some discrete set. On the other hand, this map will factor through Rn. by the assumption D, which says that the projection on internal space is dense. But right, I mean, these maps, so that's continuous. And you try to project some dense set into some discrete set, which will contradict the continuity. So that's A. B. So again, suppose not. And we have some rational subspace which is contained in Rn. Then we look, okay, so we look again at the map Lrn, which we know is in injection by its assumption to the physical space. So there's supposed to be no kernel, right? So the kernel is L intersection Rm. But then we know that it contains W, which is a lattice in particular non-trivial, which contradicts this that the kernel is zero. And then you have C. So we want to show that now that there cannot be those rational subspaces associated to internal and physical space. So again, suppose we have some W, which is L invariant. Hence, it's also SLD invariant. And it's L rational. Then, okay, so since you know, okay, so you'll take some W and W. We write it as so we have two parts, the physical space and the internal space. Since we know that this space cannot be contained in internal space by assumption I, this part has to be non-zero. Then if we take the SLD orbit of W and look at the different set, SLDR, W, right? So we do know that this SLDR acts trivially on internal space. So this part is just being killed. And what remains is the physical part. Maybe I just, okay, same thing. So what's this since? So we do know that physical space has to be contained because SLDR acts transitively beside the zero, but the zero is also contained. But now you see that this space, right? I mean, since the space we assumed is L prime invariant and SLDR invariance, this set is contained in W, So we've shown that the physical space is contained in this W, which will contradict D. So contradiction of D. Okay. So that's the proof of the lemma, the only proof I give today. And from this you can deduce that Q is simple. Sorry, that L. Okay, right. So I'll again switch from L prime to L to have some Q group. And so the proof goes, okay, so we know that L has to be the minimal Q group generated by unipotence, which contains this conjugate of LDR. And now the lemma will imply that L is semi-simple. Why? So, okay, so right, since so suppose you have some unipotent radical, then you would find some subspace, which is fixed by U. Since we have, since L, the normal is U, this space will also be L in variant. But since, okay, right, so the lemma was about L prime, but L prime and curly L rational. But if we move to L, things just become rational. So, but yeah, the lemma tells us we cannot have this rational subspace. So the group is semi-simple, and then we are happy. So okay, so you have to argue that this H prime kind of has to be contained in an almost direct vector, where you can use again minimality to say that L has to be Q-simple. And now we look into some books and some papers, so here's this theorem we found in TITS. I mean, it's well known to experts, but the problem is kind of to find a good reference for this. Right? So if you have some Q-simple group, say we pass now to the simply connected cover, then there's some absolutely simple group, G, so that you find this restriction of scalar construction. And then there's a paper of Weiss, Weiss and Solomon, where they had some question to Morris-Witte, and he proves in the appendix that, so if you have, since we know that this SLDR is contained in L, you can restrict to the groups, or, there are just two possibilities you can find. Right. I see. Right. So yes. So I made the point to why it. Yes. Okay. That's very good to know. I mean, if he gives no reference, it says it's well known and known proof. Okay, so right. So now I'll go back to the Schmidt counting problem. Right, I said to count those patches. It's actually some problem about counting points, and what we have to know is that the groups we find have to be of Rogers type in the terminology of Dimitri-Kleinbock. And yeah, so far we just know for, so by work of Rogers and Schmidt, we know that KR is of Rogers type, and recently the Kelmer U using Eisenstein series, following some approach by Mohammadi-Kelmer, so Kelmer-Mohammadi. It's also true for the symplectic group. and